Hello. In this lecture, I'm going to introduce steering behaviors and go over some of their basics. So steering behaviors is a technique for managing character movement through different types of fundamental movements that are based on forces or accelerations. So it's an extension of the kinematic movements that we've seen before, but it ends up being a lot more powerful and flexible. All right, so first of all, recall that with the kinematic movement that we've seen previously, we were directly assigning velocities to the agent. So that meant we had these instantaneous changes of velocity. These were effective in accomplishing some sort of character translation through the world, but the actual agent movement did not look natural, and it can look a lot better if we could introduce acceleration. So that's the whole premise of our steering behaviors. So again, we can have the velocity change instantly with the kinematic movement, but now what we want to do is have the agents apply an acceleration frame to frame of the simulation so that we will gradually change our velocities towards whatever goal is in mind. So for instance, moving the character towards a particular goal. So the first part of the algorithm is identifying a direction we want to go, similar to what we've seen previously with the kinematic movement. But then we're going to apply an acceleration or a force in that direction. The velocity of the agent is maintained as state information. So we have this kinematic state, and that's preserved from frame to frame. It can be modified, but it can only be modified to the degree that the acceleration is able to modify it. So for instance, if you had a very slow acceleration and a high velocity, it's going to take several frames before that velocity can be redirected to a new place. So if goals change, for instance, like the agent is no longer seeking a particular goal and now seeking a new goal in an entirely different direction, it will take a few frames, and the effect you'll see on the screen is that the agent will take a curving path as it gets reoriented by this acceleration over time, gets reoriented in the direction to go. And so that can look a lot more natural, more realistic compared to maybe expectations the game player would have based on real world experiences. So for any calculated acceleration, the current agent velocity is going to be updated. So think back to our discussion of how simulations work. So frame rate or frame-based simulation, where we're updating the state of the world as if it's one fixed timestamp, and we're updating time by some small increment such that we hit like a target frame rate, say 30 frames per second. So each one of these frames, we want our agent to calculate a new acceleration based on the situation that the agent is in. So as the agent is moving, the direction relative to the agent is going to change because it's translating through the environment. So we have to redetermine direction vectors, like a relative position vector to a target or a goal. And every time we do that, we can use that to determine acceleration. And so that's as simple as get a direction, relative position vector for our direction. We'll normalize that to a unit vector. We can multiply that times, say, a maximum acceleration. And immediately we've got an acceleration vector that we can work with and apply to our velocity. Now, we don't want to allow max acceleration nonstop. This could lead to extreme velocity. So our agent could be accelerating up until the point it finally reaches the target. We don't want that typically. So the simplest thing is to impose a speed limit so that the agent can't just accelerate forever. Now, as an alternative, some games have advanced physics simulation. So this is a topic we cover in the video game design class. And with physics simulation, we might instead implement a drag. And so the drag is applied to an object that is translating. And that would mean that acceleration goes slower and slower up to the point that its balance with the drag cannot, and the end result is you reach that where the agent would reach the top speed. And so that's balancing the drag that's proportional to the translational speed, with and balancing that against the acceleration. You can have similar effect on rotations as well, so that there's an angular velocity drag. But in either case, you do want almost always a speed limit imposed on translational velocities and angular velocities. Now, in terms of what we're going to be doing with these accelerations, we could accomplish other tasks than just directing the agent towards a target. So we can abstract away or generalize that really what we can accomplish is target matching or variable matching. And in this case, we might have different derivatives of motion or the dimensions, either translational or rotational. And so we might be trying to match the agent's position with some other position. We might be trying to match the agent's velocity with another velocity. So for instance, another agent could be moving at a certain direction and speed, and we could match that. The two agents could be at totally separate positions, but they would both be headed in the same direction and speed. That might be good for like group behavior. If we had a group of agents, we might want some level of coordination. We could match orientation or angular velocity. So we can apply this approach of accelerating to all sorts of different scenarios. And that allows us to come up with lots of different types of simple behaviors. So let's first consider seek and flee. And so we've looked at similar scenarios with the kinematic movement. So in this case, we want to match, perform variable matching on a position. Now, fleeing is going to be the opposite of that. So whatever the vector towards a location of interest is, we would just want to go in the opposite direction. So we can just, in terms of determining the relative vector, we can just swap the order of the 2 points when we're calculating the relative vector to flip them. So we're going to determine our acceleration. And that's going to be the same as how we determine velocity for the kinematic seek and flee. So that's just, we're going to mention before, we're going to get the relative position vector, normalize it. That gives us a unit vector. We can then multiply that times the desired acceleration, which would normally be full speed ahead. Then really the work or the unique part of our steering behavior is how it's applied over multiple frames. And so I've got a little bit, a few different equations, a little bit of pseudocode here to explain how this works. So first we take the agent's current position. So this would be one of the statics, the metadata that we preserve about the agent. So we take this position and then we're going to assign it to the the position plus the velocity times t, where the t value, or actually a delta t, is the amount of time elapsed since the previous simulation frame. So this will allow our agent to update its movement according to how quickly the simulation is updating, and especially adjust for variable frame rate that is definitely likely to occur in a video game. So the new position is just position plus velocity times time. Now we also update the velocity. So this is stored similarly to the statics. We'll have kinematic values that are stored. And so the velocity is equal, or the new velocity is equal to velocity plus acceleration times time. Now, if you recall from your particle dynamics physics equations, you might be thinking, well, acceleration, we should be using a t value that's squared. But if you pay attention to the code here, you'll notice that when we're adding the velocity to the position, that is going to be based on the previous frame's updated velocity, which will have already been multiplied by a t value. So, it's also normally when you think of using the t squared for position or displacement, you would have velocity times time plus acceleration times time squared. Now, the reason why the code is like this, where we're only applying the velocity in a frame and then updating the velocity, which will affect the next frame. This is done partially because our t values are already small. We're going to make them even smaller if we were squaring. So the accelerations would be super tiny. You can potentially run into a problem with numerical accuracy with floating points. You get so small it becomes meaningless, especially with high frame rates. So this approach avoids developing too small of floating point values, and it is still effective in simulating velocities and accelerations. Now, next, after updating the position according to velocity and the velocity according to the acceleration, we can then check if the speed of the agent has gotten too high. So that's going to be taking the magnitude of the resulting velocity vector, and then we'll just have information stored about what's the maximum speed the agent can go. And if the the magnitude of the velocity is greater than that, then we will set the velocity to a slowed down version. So the way we do that is we get the unit vector of the velocity and then multiply that times the speed. And so that will change the magnitude of the velocity. And now, if you're actually writing this in code, you would probably save the magnitude of the velocity so to create your unit vector, rather than doing that as a separate calculation where you call some method. You would instead want to take the velocity vector divided by the magnitude, which would give you the unit vector, and you wouldn't be performing that square root of squares twice, wasting cycles. So that optimization is not reflected here, but you would certainly want to store to a variable the magnitude of the velocity. Okay, so one problem with this approach is that while seeking a target, because of the acceleration, you can end up in a scenario where you never actually get to a static target in particular. And I've got a demonstration of this. This is actually from Red Dead Redemption. And so you can see, hopefully in the video, there is a brown bear out in the woods here, is running at a very fast speed in a circle. You might not be able to see, but there is an injured NPC laying out there in the grass, and the bear is is angry and wanting to attack. But in that, at the current speed that the bear is going, and the ability to accelerate towards the target, it ends up orbiting. And this is a very common problem in game AI solutions for character movement, is that an agent that is moving at full speed and trying to accelerate towards a position just ends up going in circles. And so we can actually characterize this with an equation. So we can use a centripetal acceleration formula to determine where or what this radius is. So in our case, we already know the acceleration because we're simulating it. That's part of the steering behavior algorithm. So we know the maximum acceleration. And then we know that we're like accelerating towards a target, and we know the velocity or the max velocity. And so the equation is acceleration equals velocity squared over the radius. And so if we shuffle the terms around, because what we really want to know is this the radius that we might encounter this orbiting. Well, that's going to be the radius is equal to the velocity squared. Now, in this case, since we have a vector, this will actually be the magnitude of the vector squared, or the speed squared, over the acceleration magnitude. So in that case, we will be able to determine our radius. And so that's the minimum turning radius for the agent for that given velocity and acceleration. Now, typically what you plug into the equation would be the max velocity and the maximum acceleration. And because that's tends to be in video game, your agents are always trying to go full speed and accelerate as quickly as they can to that full speed. But that clearly identifies the problem that you can run into. So at any given point for an agent, let's say you have an agent that's facing in a forward direction. Well, and is currently moving in a straight line. So if the agent is currently moving a straight line, let's say at full speed ahead, well, you can look either to the left or the right of the agent relative to the forward vector. And if you've already calculated the radius using the previously shown equation, you can see, well, if you turn full speed to the left, there's a circle. And if you turn full speed to the right, there's a circle. That is the minimum turning radius. And any point within either of those two circles, if the agent chooses to go towards that target point at full speed and full acceleration, the agent will never get there. Now, the target is likely not to be exactly at the center point of either of these two circles. So what you would most likely see is a precessing, meaning it's kind of like a spiral graph looking pattern where the circular path that the agent would be taking over time would wobble around the target point, but still the agent would never get there. So yeah, any point within the circle you can't get to. This visualizing these two circles for the minimum turning radius, either left or right, also is a good way to think about the instability of actually having the agent cross over a point, like a single point, not without a capture radius. So we've previously talked about why or that we want a capture radius because of like numerical accuracy issues. Well, this sort of demonstrates the numerical accuracy issues, because as an agent's moving forward, let's say it's aimed exactly at the point it wants to go at. Well, that point is going into a more and more narrow spot between these two circles. And if there's any sort of rounding error that bumps that point either to the left or right, and it accidentally ends up falling inside the circle, the agent won't be able to get to it if it stays at full velocity and full acceleration trying to get to the point. So you just keep circling around if you don't perfectly run over the point. And so the solution is you either need the agent to slow down or move away and come back if there is a target that's within the circle. Now, of course, you could also have a large capture radius on the circle to just say that it's been successfully visited, and that might be sufficient in some situations. So we might have, rather than seeking a target, we might desire to have the agent arrive at a particular location. And so in this situation, that means that the agent can only stop on a point by accelerating, or rather decelerating, to reduce the velocity just the right amount such that the agent stops on the point or within some epsilon. So this is often achieved by determining a slowdown radius, that once the agent is within the slowdown radius, there will be a linear interpolation, or lerp, that is calculated going from the maximum speed, because that's the fastest the agent could be going, and we'll scale that down to 0 according to the distance. So a distance from the point of 0 would be matched with a velocity of 0, or speed of 0. And if you were on the outside or just on the edge of this slowdown radius, then your agent would be going at maximum speed. If it was half the radius, it would be 50% of max speed, and so on. So it's just a simple linear mapping, and that would be the target velocity for which the acceleration is trying to achieve. So an acceleration would be applied to the velocity to get to the target velocity. Now, this can create a situation where if your slowdown radius is not the right size, you might actually exceed the maximum acceleration allowed by the agent. So you have some target velocity, and you can calculate, well, what acceleration would be needed to achieve that target velocity, and it might be beyond the max acceleration allowed. So in terms of defining the slow radius, you could just fiddle with it and through testing get it to where it doesn't overshoot. But you could also solve this directly if you refer to your introductory physics that you've taken before in high school or freshman college. You probably have seen this, simple particle dynamics equations for what distance would it take at some particular acceleration to go from one speed to the next. So you can just find the appropriate equations, and you can determine for yourself what that slow radius should be. So that's something that is probably worth the effort to determine if you're implementing an arrive steering behavior. Now, in addition to the slowdown radius, you might want to also implement a capture radius like what we discussed for kinematic agent movement. So if you go back to that lecture, you can see the approach used there. Now, you might have a situation where you're trying to arrive at a non-static target, though, where the agent is moving. And so in this case, the equation would be the velocity of the target minus the velocity of the agent divided by the time to target constant. So whatever that small amount of time is that's used. I think in the kinematic, we were using somewhere around 0.25 seconds. It would be the time to target. Of course, you play with that value as necessary. In the steering behavior version, like the Arrive that we're talking about right now, the time to target probably should be smaller, much smaller, like 0.1 instead of 0.25, because we're already slowing down with the slowdown radius with the linear interpolation. So this is just a last little bit of slowdown, so that once we get close enough to the target, it'll that might begin to get in the range of numerical accuracy issues. The capture radius can take over, and then it can, over a couple frames, lock the agent right onto that desired target. So we can also perform variable matching with orientation. So this is the rotation of the character. That could be, in 2D, if you have it like a 3D game that we're considering in 2D for the purpose of agent movement, this would be a rotation around the y-axis typically, and so that will be some angle that we can use to represent the orientation of the agent. So it's the same basic algorithm as Arrive, but we're working with orientation and angular velocities and angular acceleration rather than positions. So the general technique is very similar. And we'll use a slow down angle and a capture angle. The concept's very, very similar, but where things get a lot different is that angles, when you rotate around a full 360 degrees, you start over again. So we actually define our angles as negative pi to pi relative to the current facing angle of the agent. So wherever the agent is looking forward, we can rotate negative pi or pi to get to the opposite facing direction. So you could pick either left or right to rotate. It doesn't really make sense to talk about a rotation any further than that, because you generally want to talk about what's the shorter of the two directions to go. So a rotation, say, just past pi, you would actually want to go the opposite direction to rotate to get there. So that is something we need to consider and build into our line, is to define our current phase, our ability to rotate. It needs to be defined as either negative pi or pi relative to the current facing direction. And we can also do velocity matching, and we've already seen that with the capture radius, just for over a small period of time. But we can do this for other scenarios too, like maybe an agent that wants to move in the same direction and speed as a buddy moving in a group. That would be a situation for that. And it can be seen in the Boids implementation, which we will talk about later, for flocking. So like a animal-like group behavior. And so this is basically what we did before with the capture radius. So it's just the target velocity minus agent velocity divided by the time to target. And then we will want to make sure that our calculated acceleration that will test to see if it's too big. If that's past our maximum acceleration, then we will reset it or clip it so that it's only the maximum acceleration. This allows us, or at this point, we now have some basic steering behaviors defined. We have seek and flee, and arrive, and opposite of arrive is also flee. We can align with positions or angles. There is velocity matching. So from these basic steering behaviors that we have, we can create other sorts of more complicated steering behaviors, which we're going to look at shortly. But before we get to that, I do want to discuss an alternate steering behavior design that can also be pretty effective. In fact, you could build it from some of these techniques that we've talked about so far. Now, the basic idea is that we can lock our orientation and direction of velocity together. So what we've seen so far, the orientation of the agent can be completely independent of the velocity. So you could imagine, say, walking to the side but facing one direction, like a strafing sort of movement would be possible with what we've seen up to this point. But in a lot of cases, it might be desirable to lock the two together so that the orientation and direction are locked. So that means that character always faces where it's going. But if you do that, you can get some interesting results if you have the agent's angular velocity and the resulting orientation you get from applying that velocity. That's going to dictate the direction of translation. So when the agent orients in a particular direction, the only direction the agent can go is forward in that facing orientation. So I'd say the main advantage of that approach is that the agent will never appear to be sliding across the ground. Now, certainly if you have a game where agents are strafing, that would be appropriate. But in a lot of cases, what you can end up with is what looks like the agent just sliding in a scenario where it doesn't make sense to be sliding. So I've got a little simple example here. This is from Unity using their NavMesh agent, which is based on a simple steering behavior implementation. So this is the minion character. And you'll notice, so that translucent blue cube, that's like a waypoint. So the agent is seeking that. It's making no effort to slow down to reach it. It's just running through, and once it hits it, a new waypoint is identified, and the agent is then heading in that direction. So there's an acceleration applied. Separately, there is an angle align behavior being applied to orient the character. But you'll notice that the minion starts to move towards its next waypoint, which is off screen, starts to move there before the forward facing of the minion has finished turning. And it looks kind of strange because it's like the minion is just sliding on ice, even though it's wobbling. It really kind of stands out and can look, it can have kind of a poor quality animation look to the game player when you see this. So if instead we required the agent to always orient towards where it wants to go, in this situation, what would happen is, assuming the agent maintains the current like full speed forward, it would start to turn. It would take like a wide circular turn, and that would probably look a lot more natural. So the way this would be implemented is the agent first attempts to align with the relative vector to the target. So we get that relative position vector. And then we use that to generate the target direction for the alignment, so that we're applying an angular acceleration, gradually rotating the agent to either the left or right, depending on whichever is the closer angle. And then decelerate as it arrives at the final correct facing. Now, during the course of this rotation, which will probably take multiple frames, especially if the target is significantly different than the current agent's facing direction, so it'll accelerate over multiple frames, get to facing the right way. We can have the agent, in the simplest case, just move full speed ahead all the time. So again, we will end up with these wide turns as the agent is accelerating towards aligning the facing direction or orientation. But we can also implement a more advanced version that's not going to have these extreme wide turns. So there's two parts to this. One is implementing a turn-induced deceleration, and the other is implementing a variable forward acceleration. So we're not always going to be accelerating full speed ahead all the time. Instead, it's going to be dependent on where our target is relative to the current facing. So I'll go over how this would work. So when an agent is moving in a particular direction and then begins to turn, according to this alignment towards a target, well, that new vector we can use in comparison to the previous frame. And the idea is we take our current, like the newly updated velocity, and we can project the previous frame velocity, or let me step back, the new direction for the velocity. So we have like a unit vector direction that the agent has just turned towards. That's the direction that where the forward vector is now facing. We project the previous velocity. That would include both the direction and the magnitude. We perform a projection onto that new facing direction. What's going to happen in that situation? Let me show with the mouse what I'm talking about in the picture here. So this green arrow, that is depicting where the unit vector is pointing for our new facing. And that was derived by applying our angular acceleration as we accelerate the angular velocity to rotate towards the target facing. That's where we ultimately want the agent face. So I'm saying that previous frame was facing down on the screen, and the new frame, we're now facing a little bit turned to the agent's left or our right. So we can project that previous velocity onto the unit vector of the new forward direction. Now that's going to end up being shorter. So if you think about, all right, we take a right angle off of that new unit vector direction. That's where we're going to project onto the previous velocity. And what you're going to end up with is a shorter projected vector than the previous velocity. So the rotation that was applied results in a deceleration in the form of this shorter velocity. Now that's, you don't need to clamp this. You just directly apply it. You just say this was an acceleration that was specific to the rotation. So if you think of like a car turning, the car, you start to turn the wheel, which turns the tires. The tires dig into the road and introduce a deceleration. So there's that friction there resisting the forward direction and then redirecting it, but there's going to be some energy lost in that. Now in a car, we are going to keep accelerating to hold speed, or close to holding speed typically. So we can do the same thing with our agent. So once we've got this new shorter velocity vector that was shortened because it was projected onto this new direction, we could immediately reclaim that lost velocity through acceleration. Unless we can turn so quickly and the acceleration, linear acceleration of the agent is slow enough that it can't catch up over multiple frames, then the agent will slow down. And so this is something that you might desire. So you tune the parameters of the agent to get the effect you want. So you can have the agent just always trying to accelerate to regain the lost speed that was induced by the turning, or you can further refine the acceleration by comparing the desired target direction to the current facing direction. So we can perform another projection. So we can figure out the desired velocity, which would be full speed towards the target. It's going to take a while for us to get there, but that would be like ideal if we could get to that point. And that's depicted with the blue vector. That would be a full speed ahead there. And now we're not quite turned to face that yet, but we can project that onto our current forward vector, and then we can use that as sort of like a rule of thumb that, well, we don't want to accelerate much while we're not facing the target. We only want to accelerate a little. So basically, what you get from that is you can avoid big, wide, sweeping turns. You're sort of taking on this strategy of, well, let's get turning more before we get moving forward, because otherwise we're just taking the agent further away from the target. So you're going to minimize, and as those two vectors get closer together, the projection is going to get closer and closer to the full length or the full speed ahead vector. So you can use those two strategies together, and what you end up with is like, let's say an agent suddenly has a new target and it is facing in a completely different direction. The agent will tend to favor turning in place, like putting on the brakes and turning in place. And you can, in fact, you can even make this work a bit like, say, a car that's driving. You can have the agent, well, when you perform the projection, if it's a wide enough angle, you'll actually be projecting onto the negative direction of the vector, and therefore you can have the agent go backwards. So normally you might have like a conditional logic that say if you have a negative, well, just don't have any acceleration, translational acceleration until the agent turns more. But you could have the agent actually take advantage of that negative vector, and if you allow it, have the agent back up. And then it'll back up while turning, but then it'll go slower and slower as that angle gets closer to flipping the velocity to the other side. You'll hit a target of zero speed just briefly, and then as you turn further, now you can start the agent. It will accelerate more and more in the facing direction, and then it'll get closer and closer to the target. So I personally like this approach to applying steering behaviors to agents. I think it looks better than the other approach where you have the independent turning and translational acceleration. But there are certainly cases where you would want them to be independent, like if you have an enemy agent that's strafing while firing at a location, perhaps, that sort of thing. Now, if you're using the turn first steering behaviors, you will need to make a few adjustments. One in particular is if you're determining the minimum turning radius. Well, the orbit, the orbiting, the minimum radius of the orbit is going to be the speed, the maximum speed divided by the maximum angular velocity magnitude. So the angular speed max, or so translational speed max over angular speed max is going to determine the orbit in that scenario. And that's just because we've defined motion a bit differently, so we need to calculate differently that radius. Now, if we have that fully advanced version of turn first steering that I talked about, where there's a variable acceleration according to the angles and using the projection. Well, that already can basically avoid the whole problem of the orbit radius. You're not going to have these wide swinging turns. You're going to tend to turn in place more. And therefore, the orbit problem you're not necessarily going to have. And then also, because you do have the locked alignment with the direction of velocity, that means certain types of combinations of steering behaviors or blending of steering behaviors, and we're going to talk about that in the future. But that's not going to be possible for all the scenarios that you might imagine, just because our agent has limited freedom because we've tightly coupled the orientation with the velocity. The certain things it just can't do, like walking sidestepped. So next up, we're going to look at delegated steering behaviors. So we're going to build off of the fundamental or basic steering behaviors we looked at last time and create some new ones. So we previously defined seek, align, and velocity matching. Basically, any of these variable matching steering behaviors can be used to build more complicated delegated steering behaviors. So one that we might want to develop is pursuit. So this is like seek, but we're going to introduce prediction. So basically, just come up with a new position to seek, but it's going to be defined by where our target is moving. Say we're chasing after one agent chasing after another agent, or perhaps chasing the player. So this calculation needs to be made every frame because every frame our target is going to be updating and possibly moving. So we're going to need this calculation to be efficient, and therefore approximating is probably okay as long as we're converging on the solution as we get closer. So we don't need a perfect solution. We can come up with something simpler to calculate, but is still effective. And so the way that we could implement this is to calculate, well, first based on a zero acceleration or constant velocity assumption. So we're extrapolating our target's position according to its current velocity. So no acceleration, that means no changing of direction or course that is heading on. And the other thing we're going to do is rather than calculating a precise intercept, which we could do with the constant velocity, we could figure out exactly where our agent should be aiming for an intercept. But we don't need to do that. Instead, we can use a heuristic, and that heuristic is that we're going to consider the current distance to the agent at its current location. And we're going to say that, well, that distance can be the basis for an estimate of time that it'll take to get to the target, or at least in the neighborhood of the target. And so the way we'll do this is we'll take the length of that position vector, or the distance, and we're going to divide it by the agent's maximum speed. That tells us how much time it would take to get there, approximately. Then what we're going to do is plug that approximate amount of time it'll take us to get in the neighborhood. We're going to plug that into an equation of motion for our target that's just assuming constant velocity. So that would be future position is equal to current position plus time times velocity. What that will give us is an updated future estimated position of our target. And that's what we're going to aim at with seek. And so it's a very, very straightforward calculation. And again, of course, this is being calculated every single frame. We've kept things simple, straightforward to calculate. As we get closer to the target, assuming that's possible, meaning like our agent that we're writing the code for can actually gain ground on our target. If that's the case, then this t-value is going to get ever smaller as we get closer. So even if it's wrong in some way, so it could be like maybe the target is heading straight at us, which would mess up the t-value, or it's heading directly away from us, which would also cause that t-value to be wrong. But it's okay to be wrong because this will still converge. Also, you can evade by fleeing from the future target, and so it can be useful to recognize where the enemy is going to be in the future. Assuming you're trying to get away, then you want to dodge that position, which would be more effective. So with this pursuit behavior, we're going to get a more effective or more efficient route over time. And so you would see something like what's depicted in this figure from Millington, his game AI book, figure 312. You can see that the pursuit route would not involve such a steep curve, which would tend to be always approaching the moving target from behind because it's always moving to an old position. So it'll avoid that and intercept the target more quickly as opposed to just seeking the current position. Now with prediction, you need to watch out for some situations. So one is that you can end up with extreme predictions with a very large look ahead t-value that is very unlikely to be correct because a target will tend to only be following a certain path for a short period of time. So this you'd probably set empirically, just test things out until you come up with a good value. Don't look ahead any further than a certain amount. You could also consider looking at where the target could end up relative to what's known about the environment. This works especially well with nav meshes. So if you know where the target is on the nav mesh, you know its current velocity, well, you can cast a ray along that current velocity based on velocity times our look ahead t-value. That's going to define the length of the ray that we're going to cast. And so that will tell us, well, if we get a hit against the edges of the nav mesh, then we know that, well, clearly that's impossible. The target would have hit the walls of the obstacles that define the nav mesh. It would have had to have changed direction. So that can lead to a strategy of maybe abandoning prediction in that case, or clipping the extrapolated future position along that cast ray so that the point of collision would be the where the agent heads towards. We can also face a vector position. So this was mentioned for the steer first strategy for steering in the previous lecture. One thing I didn't mention then is that if we don't have an angle identified, we'll need to come up with an angle from a vector. And the way to do that is using the x and y components of our vector. We can plug that into ATAN2. And this is a special implementation of ATAN that, or arctangent rather, abbreviated to ATAN. But it's a special version that tracks the numerator and denominator sign to figure out what what the sign should be on the angle. Otherwise, if you just were using ATAN rather than ATAN2, then you would just have a positive angle, and you wouldn't know the proper the proper turning angle, because you would lack that information. Now you could figure it out by analyzing the signs yourself, but it's already implemented in ATAN2. It's available in almost every math library and game engine, so it's the simplest thing to do is to use ATAN2. Looking where your agent is going, this is a simple one to do. You just align towards the current velocity. So it's basically face, but instead of using a relative position vector, you're just using the velocity. So still using the ATAN2 with the x and y component of the agent's velocity. We also can define a better version of wander than what we saw with the kinematic wander. And the way this works is kind of clever. You put a circle. You can't see the circle in your game, but it's a hidden or an imaginary circle in front of your agent by some offset in front. You place the center of this circle, and then the circle is defined by a certain radius. Then there is a target point, perhaps initialized at the furthest point on the circle away from the agent, or maybe the closest. Usually you would pick one of those two locations. And then each frame, the target rotates around the circle. And we could use a random function, perhaps the same as from the kinematic wandering, that you can refer to if you want to see that random function. And that will define how much rotation left or right occurs each frame. And so that target is used by the agent to decide where to face. And the end result is that you can improve the sort of frenetic changing of direction, because the target has to rotate around the circle. And so even if it changes direction back and forth quickly on the circle, if it doesn't rotate very much, that's not going to have a big impact on the steering direction of the agent. So you'll tend to have these kind of gradual meandering turns of the agent, and it looks much more natural, especially like for a human NPC that's just casually walking through a town or a village. And so once you've determined this target and you updated every frame with the random movement, you can apply face to get the angular acceleration to move towards facing that particular direction. And then you apply the maximum acceleration forward. So whatever the fastest that the agent can go. So this is kind of like the turn first steering behavior that we talked about in the last lecture, except it's just specific to this wandering. Path following, this is another one where we had a very simple implementation described for kinematic movement, but now we can come up with a much better and smoother animated version for steering behaviors. So in order to implement this, well, first we need a path. And so this might be a linear path defined by linear line segments. So we will have different points, endpoints for each segment that are chained together, one line segment after the next. So we need to be able to find the nearest point on the path, which is this, at least for line segments, is finding the nearest point on a line segment for all the segments, and then pick the nearest of all of those potentially, or in a naive implementation. We could, however, improve upon this by using some kind of space partitioning scheme. and identify a neighborhood of the agent, and then select a line segment or a small number of line segments in the neighborhood, and then perform the nearest point on segment test for that subset of segments. Once we have identified that nearest point, we can pick some point a little further down the path, but maybe based on a velocity in time or some fixed distance, and that would actually be what we steer towards. So a lot of the complexity of this implementation really lies with how we've defined our path and the equations that we use for determining the distance to the path, and the space partitioning that we likely would want to use for anything but a simple example. And of course, the type of path is going to have a big impact as well. So line segments maybe are easier to work with. We've already seen a way to find the distance to a line segment in terms of like computational geometry calculation. We could consider Bezier splines, which are curved paths, and which do tend to be popular to use in games, even though there is added complexity. Having curved paths, the aesthetics of curved motion can be beneficial, so they're popular to use. That's kind of beyond the scope of this class, the specific implementation of this nearest point on path, but just be aware that we could generalize our path, so whether it's linear line segments or Bezier splines, or some other type of curve that's going to that can vary. So we're just seeking this target that's further down the path, and this is going to be based on how the path is oriented, the data structure, so like the sequence of connected points. So we'll know like, well, what would be the next segment in the sequence. And so we could either go in positive or negative direction, depending on what makes sense for the forward direction on the path. Now, there's also a predictive path variant. And in this case, rather than find the nearest point to the agent's current position, we can extrapolate out based on where the agent is going. So some future position may be some amount of time times the velocity, and we'll extrapolate along the velocity vector to come up with a new point. So that predicted future position we will then use for determining the nearest point on the path. And then once we have that spot on the path, we'll then pick a target that's somewhere further down the path, that's actually on the path. And so that will be the seek target for the agent to move to. So this predictive path following can be smoother in terms of the movement of the agent over time. But a downside, and it really depends on the scenario, how big a deal this downside is that you can end up cutting corners. So your agent might predict a future position, and like as depicted in this figure, which is from Millington's Game AI book, figure 317, and it shows how the predicted future position might cut off a corner. So that would probably not be desirable for if you want a guard to go on a particular patrol and truly visit different points along the path, or for racing games would be another one where this isn't good, because you'd have an agent that cheats. So so that it's a compromise, and you can tune this, perhaps also just adjust your path to kind of avoid these sorts of scenarios. Now, for path following, it's very useful to store the last known point on the path. This can be used in conjunction with space partitioning, and perhaps even avoid some of the need for space partitioning if you know where you were last or your agent was last on the path, then this information can help you identify where it is in the future. You can disambiguate. So in this situation here from Millington's book, Figure 319, you can see that we have kind of a pretzel path where the path winds back and self-intersects. So it can be a real challenge to figure out, well, what is the closest point? And so we might come up with a means of measuring the distance from along the path from the previous point of different candidate closest points. And so that would be the what you actually use for the selection is the distance from the previous point to the candidate closest point. And so this is an example of coherence where we're tracking where the agent is on the path. We've seen coherence as being beneficial for space discretization as well. So for instance, on a nav mesh, it's really useful to just track where all important game objects are that the agent needs to know about on the nav mesh. And so that way you can always find the information you need within the data structures that you're working with. Another steering behavior that we can define is separation. And so this is used to separate agents, but unlike flee, we don't want them to separate forever. This is based on some threshold distance, and then if they're separated sufficiently, the agents don't need to separate further. This is good for things like crowd simulation or flocking, especially when the agents are all moving in the same direction. This can help spread out the group. So there's a couple different approaches we can take and calculate a strength of this separation force. So we could use a linear force. And in this case, we have the maximum acceleration times a threshold minus distance. And this threshold is the separation distance that we're desiring. And then so the maximum acceleration times threshold minus distance over threshold. So we're dividing by the threshold as well. And another approach we can take is inverse square. And this we're taking a minimum of either the maximum acceleration or a coefficient k over the distance squared. And so depending on which of those we use, we can come up with different behaviors, maybe where it's gets much stronger with the inverse square, much stronger really close, and then decays the further you are. So it has more of a like a smooth effect. So gradual or tiny bit of pushing when they're further apart, but stronger when they're close. So it looks maybe a bit more organic. In terms of how to calculate this when you have lots of agents, well, you could just pick the closest neighbor to calculate the separation force, or maybe you pick a number of nearby neighbors and take the sum of those forces. And then, of course, you would clip this to the acceleration max. So the sum of all those forces, if it leads to acceleration stronger than you want to allow, you just clip it. Now, this needs space partitioning and coherence as well to quickly identify neighbors. So we might have a bin queue. So divide the world up into like a grid lattice, basically, where each grid cell is a list of entities that are in that cell. And then when you're looking for a neighborhood, you look at the 8-way connected cells, including the current cell. So if our agent is currently in a cell, we'll look at the list of entities within that current cell, and we'll look at the entities up, down, left, right, and then the 4 angled directions. And so that would be our neighborhood. And of course, as agents move around each frame, we need to leverage coherence to track as they move from one bin to the next. So deleting from the queue and add to another queue. So we could also create an attraction steering behavior. So it's the opposite of separation. It's not often useful. Mainly you would use it in like a flocking group behavior. We'll look at this when we discuss group behaviors. But in this case, we'll use the inverse square with a negative k or constant of decay. And so that will just make the force in the opposite direction, pulling together. And we would probably balance that with a separation force. So if it gets too far away, we're pulling something in, but if it gets too close, we'll push it away. And that's one of the key features of Boids. We also might want our agent to perform collision avoidance steering behavior. So this would be to avoid other agents, especially large numbers of agents moving around in the same space. So we could do so by creating a collision avoidance cone. It's like actually a triangular wedge in front of the agent. And we're performing this test with a dot product. And so we're going to use the current direction that the agent is moving. So that could be we use either the forward heading of the agent, or if it's moving separate, then the facing direction. We could use the current velocity and convert it into a unit vector, and then perform a dot product with a relative position vector that's also been normalized into a unit vector. So take the dot product of those two. So again, it's the velocity dot product with the candidate entity, so probably another agent, that relative position vector to that entity. And if that dot product is greater than a cone threshold, where the cone threshold is the cosine of the half angle of our cone, then that would determine that there is a collision. And so this can work well for occasional isolated collision potentials, but it starts to fall apart when you have lots of agents. You also will see that agents tend to overreact. That's especially apparent in these two figures from the Millington book. And you'll see that based on the cones, you might have the cone angle large enough that two agents could be oncoming, say, walking down a hallway or a sidewalk, and the cone test would say that the agents are in imminent danger of a collision, even though there's actually not going to be one that occurs. You can also have a scenario where two agents moving in roughly the same direction are starting to converge in their paths, and so there's might not be avoidance in time, and the collision actually occurs because they're not able to, say, accelerate away from each other with enough warning. We can improve upon the collision avoidance strategy if we add a constant velocity assumption. And so in this case, we can now look for an intersection of the paths of two agents. So again, assuming constant velocity, so we're extrapolating along the current direction. We can do so taking into consideration the speed along that direction that they are traveling. So that's going to be the rather than the intersection of two rays, we'll instead be looking for the points of closest approach. And so that's going to be a function of not only the direction of the two agents, but also their speeds. So we're going to find the time of the closest approach, and then that'll allow us to identify these two separate points. So to find the t at the point of closest approach, we take the dot product of the relative positions of the two agents. So that would be like the position of target minus position of agent defines the d sub p vector. And then we do similarly with the velocity. So the velocity of target minus the velocity of the agent is going to be d sub v. So we're taking the dot product of d sub p times d sub v, and then dividing it by the magnitude of the d sub v, and then squaring that. So that will give us the t value. And if it's a negative t value, the entities are moving away from each other and we don't have to worry about a collision. But otherwise, what we want to do is find this future position for each of the two agents. And so we just use future position equals current position plus velocity times time for both of them, so that using their own unique current positions and their velocities. Plug that in using the t that we just solved for, and then those are the positions that we'll use for avoidance. So each agent will be avoiding the other agent's point that is derived from this closest t. In terms of implementation logic, we might need to consider scenarios where there's more than one agent that's possible to collide with. So it's best to just only use this strategy with the closest of possibly many agents. Don't try to, say, add all of the positions together to find a centroid. That will not work well. So it's best to just pick the first. The other thing is you need some special case logic to deal with the scenario where two agents are already colliding, which could possibly happen. So we also might want to avoid obstacles or walls. So in those cases, we're going to cast a ray that's based on the current velocity multiplied by some look-ahead amount of time. That look-ahead t you'll generally determine empirically, just test things out. Well, what's appropriate, but it'll probably vary with how quickly your agent can turn or accelerate away from a pending collision. And so you tune it until things look good, basically. But if when this ray is cast, it gets a hit, then you find the normal from that point that'll be based on the obstacle. So whatever, say in the case of a wall, the line segment that makes up that part of the wall, we can determine the normal, which goes out from the surface. And then that normal is multiplied by some avoidance distance, and that will so the normal is a unit vector, multiply it by a distance that will offset from the wall a certain amount. That is the target to seek, and so the agent will now be steering towards that avoidance position. And the problem with just using the single ray from the center of the object, or the agent rather, so casting a ray from that point forward along the current direction of travel, it doesn't take into account the size of the agent. And so a ray cast might miss the wall. If, say, a corner of a wall is within the path. And so a way to deal with that is to cast additional rays in the form of whisker rays, and these are often fanned out at angled, and they're shorter than the main ray that is cast. And so these shorter rays are able to detect if your agent's starting to get too close to an obstacle, and then the agent will respond accordingly by turning away from the whisker that is triggered. Unfortunately, this is susceptible to problems, most notably the corner trap. And so you can have a scenario where the left or right whisker will, when the ray is cast, an intersection is found, and it triggers a movement in the opposite direction. And what that does is then it causes the other whisker to turn into the obstacle if a corner is being approached, like shown in the figure. And so the agent will kind of wiggle back and forth slightly, just homing in on the corner like it's an intended behavior, and then just get stuck. And so this is a challenge to deal with. One approach is to make a wider fan of the whiskers. Basically, the angle between the two whiskers, if you make it wide enough, then the agent can safely turn without getting caught in this trap. But then this whiskers can end up so wide that it has trouble walking down hallways or fitting in narrow corridors. The whiskers will set off the obstacle avoidance strategy. So an advanced solution is to have an adaptive fan angle. So when there's a collision that occurs, the whiskers start to widen the angle, and then over time they will narrow back to their steady state. Now, you could use other approaches, such as with the support of a physics engine using the collision detection capabilities and testing against a projected or extruded collision volume or area, and then so that we could get relatively efficient collision detection, but this will be much more computationally expensive. And then probably a bigger problem is interpreting the collision results. So if you get a collision on a particular part of this this collision volume, then what's the appropriate strategy for the agent? And so that is there's not a clear-cut answer, and I don't think a demonstration in commercial video games that has sort of won out as the go-to strategy. So many solutions still focus on the whiskers, probably like the fixed whisker length with the dynamic or adaptive fanning out when collisions occur is probably one of the more popular strategies. So we now have a library of these delegated behaviors that were built off of the fundamental behaviors. And so from a line, we've got look where the agent's going and facing a target. There's also the seek or flee, which allows for creation of wandering, pursuit and evasion, path following, collision avoidance, obstacle avoidance. And then there's velocity matching that can be used for the end part of arriving. And then we have the force field sort of approach for separation or attraction. So this allows for some pretty powerful ways of defining our agent movement, but it's still pretty simple to implement. So next up, we're going to look at blended steering behaviors. So we've already just defined fundamental steering behaviors, and from those, some delegated steering behaviors. And now we can further mix and match through a blending strategy. So consider a scenario where our agent needs to avoid a danger, but is also seeking a goal. So we might have two different steering forces that aren't in agreement with one another. So how could we deal with that? So one solution is that we could blend the steering forces additively, or we could arbitrate. So we'll start first considering adding them together. So we might just add them directly. So that would just mean adding the xy terms of the two vectors, and then you'll get a vector pointing in a new direction. And so we could just use that as our acceleration capped to our max acceleration to head to, or we might do some sort of averaging strategy. So maybe each has a contribution that is not the total length of the vector, but maybe some fraction of the vector that's added. But in the figure shown here, we see the agent trying to get away from a danger, but also trying to get towards our goal, the fish. And so the idea is that when these two vectors are combined, we might get something that's a blend of the two, something in between, and the agent heads towards that on the given simulation frame. And then the next frame, we recalculate these vectors and their contributions to the blend and repeat this over and over. And the idea is that we would get a path that if you look at the whole history of these the calculations for the steering behavior movement, you would end up with a path that looks like it's optimizing to avoid being near the danger, but also going towards the goal. So in terms of additive strategies, well, one is we can just take the sum of the forces, and we would need to impose a maximum acceleration. So we add them up. We need to make sure that those don't add up greater than the maximum acceleration allowed, and that would tend to be the case because the any of these steering behaviors in isolation, the agent will tend to go at full speed towards it. So we're going to be clipping the length of that vector, the resulting vector, when they're added up pretty much all the time. Now we could also take a weighted sum, and this is each force generated will have associated with it a weight that's multiplied by. We don't need these to add up to 1. It could be something else. You could normalize them by dividing by the sum of the weights, perhaps, but that's not necessary because we can still clip them. The weighting is really more to set a relative bias. So if, for instance, one force or one acceleration is weighted higher than another, then it will have more influence. So we might have, say, a bias towards staying away from the danger more so than seeking the goal, or vice versa. And we could, for any defined steering behaviors, we could just play with those weights and get different different patterns of behavior, say personalities of different agents. So they might be using the same steering behaviors, but we play the weights such that one's more afraid of dangers, or one is more willing to go towards the goal even in the face of danger. And we could possibly even make that dynamic, perhaps tied to health. So the weights could vary according to the state of the agent. So there's problems that you run into with blending. You don't always get the sort of ideal scenario that was shown in the first example. You can have your forces balance out, like shown in this figure. And so in this case, both the goal and the danger are in this same direction relative to the agent. So that means we have an attractive force for seeking our goal, and then also this repulsive force for staying away from the danger. Those can balance out or cancel out. And in this scenario, this would be an unstable equilibrium. And it's kind of like um, balancing a broomstick in your hand. There's going to be a tendency in an unstable equilibrium for the agent to slide just a little bit left or right, maybe related to numerical accuracy. And just a slight nudge one way or the other can then get the forces to no longer cancel out perfectly as zero, and the agent will begin to accelerate either to the left or right, depending on which way it starts to slide. Now, that's not to say that just because the agent can break out of this, that it's not a weird thing that like the game player might notice that the agent does. So it's still, I would say, an anomaly that it would be nice if it could be avoided. But there's also stable equilibrium, and so we can see this demonstrated in the next figure. So now we have two repulsive forces that the agent's trying to avoid the two dangers. So we've got these two separate vectors that now stabilize the potential for sliding to the left or right based on any sort of numerical accuracy induced instability. But we still have that attractive force for the goal. And so somewhere along that line, the forces would balance out to zero. So the agent can just get stuck there at that equilibrium point indefinitely with the forces all balanced out to zero. There are some other problematic cases for steering behaviors as well. Even if the agent's not getting stuck, the agent can make poor decisions, and it can be pretty much impossible to design steering behaviors such that steering behaviors alone, such that you get the desired complicated sort of behavior you might need for your gameplay. This is especially a problem in constrained environments such as indoors or in canyons. Scenarios where you have lots of agents can also create problems. And so what can happen is that all these constraints lead to lots of steering forces, and this will create these failures that will impact the gameplay negatively. And so if you think about how steering behaviors work, they're going to act most strongly to local influences, and that creates this nearsightedness so that other points of interest that might influence the agent through steering behaviors, they're not going to be able to influence these more nearsighted reactions. And so I'll show you a few figures from Millington's Game AI book here. So these are figures 335, 336, and 337. So these scenarios demonstrate blended steering behaviors where things won't work out the way that the designers of the AI would probably like. So one is pursuing an enemy, maybe trying to, in the case of pursuit, this would involve prediction. So trying to steer and aim ahead of where we're extrapolating the position of the enemy. But as that turning towards that future position occurs over the next few frames from what's depicted here, the wall gets in the way, and so the um, the raycast sort of test that would be performed will get a collision on the wall. Will with the along the normal of that collision point on the wall, will define an offset for wall avoidance, and the agent will need to be steering towards that. So what will happen is the agent is starting to turn towards the enemy, but then the wall suddenly gets in the way, and then turns away in a big circle, and not a very efficient route. Instead, what really should happen is the agent understands that the wall is there and steers such that it can go around the wall and follow the enemy. But that, with simple steering behavior additive blending, that's not going to happen. We could also consider a scenario with a doorway. So the agent is trying to follow a target, maybe that passes through a doorway. But then as the agent is following, the agent quickly goes to the doorway. That raycast, again, looking for wall collisions, gets a hit, and then it turns away and is never able to turn into the door. And so we can have these different sorts of scenarios like depicted here, where the agent's just not going to be able to deal with them. So what's the solution to work with steering behaviors that might include these blended steering behaviors? So what you need is higher level planning. This could be in the form of path planning, but probably also some form of higher level decision making, like a reactive decision making strategy, such as maybe using a finite state machine, perhaps, or decision trees, rule-based systems. There are a number of different strategies that we will look at in the future that we could use to drive steering behaviors, and then recognize different situations where we switch to new strategies and use some new set of steering behaviors. But before we get to those different types of planning systems, we can consider a small variation to the blending that we've talked about so far, that begins to introduce some arbitration, and that is priority blending. Now, this is beginning to blur the line between just our basic steering behaviors and integration of some sort of reactive decision-making system. So this is one that you could actually implement by leveraging something such as like a rule-based system, perhaps. But the priority blending is based on the observation that many of our steering behaviors we've seen so far, at least some of them will return a steering force only in the presence of a stimulus. So like obstacle avoidance, it doesn't return a steering force if there's no obstacle there. There's nothing to return, so it would have no impact. It's only when the obstacle becomes imminent in terms of like a collision that it then begins reporting this corrective force or acceleration. So these also, the ones that tend to be variable like this, they also tend to be very important in the scenarios where they trigger because of imminent threat. Now, if we just blend these all the time with other forces, like say a goal-seeking force, well, the avoidance force can become diluted by the other forces, basically becoming less effective. So maybe the fact that we're blending it's going to make it more likely that there's still a collision that occurs. So with the priority blending, we can prioritize steering behaviors that activate above a certain force threshold. That this would be a threshold you set in code empirically, or if it's just anything over zero, you would maybe have just a small epsilon value, but it could be a larger value perhaps in some implementations. But you can apply this to a single steering behavior or perhaps a set. So a set meaning that a group of steering behaviors that are blended maybe additively. And so if that collection doesn't generate above the threshold, then we skip to the next set. And so you might have a rather elaborate sequence of evaluation of like set A, set B, set C, and so on, checking to see if those collectively activate, like the sum of the forces activates above a certain threshold. If it doesn't, you go on to the next one. So the priority is implied by the order of evaluation. So the first one you evaluate is the first one that can win, directing where the agent goes. But if it doesn't activate, then the next set has an opportunity, and so on. So this can immediately avoid unstable equilibria. We saw before that with unstable equilibria, they tend to destabilize and fall apart, at least the agent being stuck, but the agent's still briefly impeded by this. And so priority blending can just immediately avoid this sort of scenario by, say, prioritizing avoiding the obstacle. So there's no opportunity for the forces to cancel each other out or balance out. It can also avoid some stable equilibria if the basin of attraction is small enough. And this is because you'll tend to have like an obstacle avoidance that will move the agent away. And then once it moves far enough away that it's no longer activated, then something else can be prioritized, such as going to the goal. But if the basin is huge, the agent will move away, but then head right back to the goal. So you kind of end up in a vicious cycle. So the agent's not stuck at a fixed point, rather it's stuck in a pattern of movement, of like going in a big circle over and over. So priority blending isn't like a solution to all problems, but it does help. And you still have issues with constrained environments. And of course, stable equilibria where you have a large basin of attraction would also be an issue. But otherwise, the blending is just further empowering the strategy of steering behaviors. There's a lot that can be done with steering behaviors, and where there are deficiencies, a lot of those deficiencies can be addressed with higher level planning systems. So next up, we're going to look at steering behaviors from the context of animated characters. So for instance, characters you might find in a 3D video game that walk around, run and jump and so on. So first of all, I want to give just a brief introduction to how animation works in a lot of games. I'm not going to go into the same level of detail that I go into in the video game design class, but just try to give you an idea of what's involved. So animations that you have in games that involve, say, a walking or running and jumping sort of character, we're going to have movements that you might think of as like a puppet. So the legs bend at the knees and rotate at the hips, the arms swing, and so on. And we might have different animations in a loop form for walking and running and jumping. And those animations that involve the limb movement, well, they can also include translation and rotation in the environment. And this is generally referred to as root motion. So this is translations and rotations that are embedded in the model itself. So these are often defined with skeletal animation, which is a topic that you can easily find information on online if you're interested. But the root of the skeleton is usually like the hips of the skeleton. And so that is where all this translation and rotation information is stored. So this is very common in your typical 3D game, and it is largely used to drive the movement of agents or NPCs in games. And furthermore, all these different animations like the walking and running, they can be blended together. So you have these different like separate loops of animations. They get blended together, which affects the different poses of the limbs, like the bending of the knees and rotation of the hips and arms and all that. And they get blended. So like the walking can be blended with running and make a jogging animation, and variations in between. So you get like nearly infinite different combinations of these movements, and that can drive the animation of the character. It's like the performance envelope topic we'll look at a bit more later and related to steering behaviors, but it defines what the character is capable of just by the set of animations and how they are all blended together. Now, so far what we've seen with steering behaviors is that we are defining the movement of the agent programmatically. We've written code to update the position and the rotation, and then we're updating the velocity according to these steering forces that we're calculating. But with an animated character, we don't have that sort of direct control, especially one with this root motion and blended animation. All of those values are outputs from this animation system that's running. So how can we make that work with root motion? And so this is a real challenge. So what you would probably want to do is, well, you can still calculate your steering behavior targets, like where you want the agent to move to, rotate towards, and so on. But how do you tell this animation system to do what it needs to do, to like seek a particular target or align orientation? And well, generally the way these animation systems work, like say in Unity, is you pass to the animation system that's already been initialized with all the different animations it's going to be using and blending together. You pass to it some animation parameters, and these are often normalized to a scale of like -1 to 1, and that might you might have different dimensions for, say, rotating left and right, or translating forward and backwards, or maybe moving left and right rather than rotating. It kind of depends on the character. So what you really want to know is, what is the result? What is the output of the animation system if you pass it these parameters? So you can tell it will turn a little bit to the left or a little bit to the right. So one thing you could do is just kind of fit a function to what the animation system does, and you just kind of do this empirically. So this sometimes works. I've done it before. In fact, I'll show a demonstration in Unity in a few slides here where I've done that. But when you have complicated possible animation blends, this can be challenging. So another strategy is you can create a lookup table. basically, you can say, all right, if I want the agent to, from its current position, end up at this spot in the next frame, then what would be the animation parameters that could do so if it is possible? And so you could actually create this table through some analysis of the animations. Probably this could be automated. So you would say that, well, if you're blending this animation and this animation, if that's what the animation system is doing, like blending some set of animations, you can say, well, if you're blending these with these weights, you end up at a certain location. So you could work backwards from that. So like what would be the animation system input parameters that led to that new pose, whether it's related to translation or rotation or both. And so that is a possibility. I'm going to just kind of keep it high level discussion now because this can get kind of complicated. But you can make this sort of lookup table. Now this can be further complicated because a lot of times the different blending possibilities, you could tell the animation system to immediately go to any of these, and that would be like instant acceleration to these different velocities. And often that's not what you'll want. So the input parameters will perhaps be filtered. And so the filtering is basically an acceleration in practice, because you can't move. You can think of it as like these animation system input parameters is like joystick offsets. So like pressing forward or backwards, left and right would be in probably like a range of values. So like press all the way to the left would be -1, all the way to the right would be 1, forward, all the way forward is 1, all the way back is a 1. And so that's like an X and a Y, on these normalized scales. And then 0, 0 would be the stick at top dead center. So those are the sorts of parameters that you're trying to recover through this lookup table. But if you quickly move the stick on a joystick from like one angle to another, those might be filtered such that it takes some amount of time before the parameters settle on the new location. So that'd be like an acceleration. So that's something else that you have to take into account, is that there is like a maximum acceleration for which you can change these input parameters. And you'd have to take this into account as well as you're looking up positions in this lookup table. But if you do this, you can come up with something that works fairly similar to what we've done so far when we've had direct programmatic control of the agent movement. It's just we have this added complexity of something that's almost like a black box, not quite, but the animation system just adds a lot of complexity. And we need a way to account for how that defines the movement in terms of like if we're trying to align or accelerate to a position, we're basically have the challenge of getting the right parameters to the animation system to go where we want the agent to go. And we can improve on this sort of table approach by interpolating between positions, like table cells. If we have a position that's not a perfect match in terms of like a movement, let's say, then we can interpolate between the cells in that neighborhood. So maybe the cell, we're in between cells in the vertical and the horizontal, so that we might take the average of 4 cells. And so that's just like a linear interpolation, and that can improve the quality of of the result, which again would be the parameters that we want to pass to the input system to get the desired output behavior. All right, so next up, I want to switch over to a little demonstration of the simple approach of just fitting a function. So the function, the fitting of the function for this animation system is just based on orientation. So these are robot agents that they will orient in the direction they need to go. So they're just following from one waypoint to the next. And so that they need to be able to turn accurately and face the correct direction. They're just always going full speed forward. Actually, I take that back. I think they will turn in place if they're not close enough to facing their target. So say they have to double back where they're going, they will just turn in place. But that's just using a simple dot product test. Let me switch this back to full screen here, and I'll hit play. All right, so you can see this robot agent. So the camera focuses on just one of them. We also show the path that the agent is using, and this is using the Unity Nav Mesh. There's lots of other agents that I have running around. So you see there's some that are similar to the agent that the camera's focused on. They just happen to be running a different route. And then there's a few special ones that just to make things challenging, they look like they're wearing a giant robot dress. So those agents, they're big and they get in the way. And so it's demonstrating some of the efforts to avoid obstacles. And honestly, it doesn't work all that well. The implementation in Unity, and it could have improved. This is running in an older version of Unity, so the NavMesh framework and the NavMesh agent could have improved. But the way that this works is there is so it's using NavMesh agent, which has its own vehicle performance, like its turning rate and acceleration and so on. And you can't see it. It's attempting to move each frame, but it's like a hidden object. And then the animated characters, which are all controlled by root motion. So the animation system completely drives orientation and rotation of the agents, as well as the translation, moving through the environment. So the animation system's fully controlling that, and what's happening behind the scenes is there's a little simple algorithm that's telling the animation system to try to go to where the agent goes, the NavMesh agent. And then each frame, the NavMesh agent gets reset. So if the 3D animated character is not able to perfectly follow the hidden NavMesh agent, it doesn't matter, because the hidden NavMesh agent gets reset. And that, by the way, is actually the recommended strategy that that Unity suggests in the documentation. Is if you have a root motion character, to have it follow in that fashion. Now, I haven't. There may be new tools provided by Unity. They actually have a new updated NavMesh toolkit. I just haven't lately checked that out. This I made several years ago. But one of the challenges here is when you send the animation parameters to turn, say, left or right. Well, you can overshoot. If you pass the wrong parameter, you'll end up turning too far to the left or too far to the right. And that means that if you do that, you won't be heading on the correct heading. In fact, your agent will kind of look like they're drunk or something, kind of swerving back and forth, never heading straight in the path. They'll usually eventually get there, but they're just swerving back and forth because they can't uh, dial in the turn rate. And so I just wrote a little function that had tunable parameters that allowed me to scale the turning rate, and then I just played around with it until I could get it to work. So and then these agents, in terms of deciding where to go, and you might notice they occasionally will stop in place for a few seconds. That's all driven by a simple state machine. So there's actually a state machine that is driving the move from one waypoint to the next, and exactly what they do when they get there. But again, all of these agents, they're moving based on steering behaviors, but the actual translations and rotations of the agent in the environment is all driven by the animation system. So the challenge is figuring out what are the correct parameters to pass. All right, so I'm going to stop there, and in the next video we will summarize steering behaviors. All right, in this video, we're going to wrap up looking at steering behaviors. We're going to first consider some applications of steering behaviors and then conclude with a summary. So first of all, I want to discuss creating unique agents. So we've seen all these different ways that we can apply steering behaviors to create different sorts of compelling patterns of movement for an agent. So in terms of creating a unique agent, of course, we can select appropriate behaviors for the particular activity of the agent. And maybe to further make behaviors unique, we might blend in we might blend in steering forces that aren't necessarily related to efficiently performing an activity, but maybe something to define character or just look unique in terms of motion or movement. So for instance, we could add just a slight perturbation based on like a wandering. So the agent could be seeking a goal, but we add something that causes them to move just slightly. And so that maybe that would make it look like more of a predator type of creature, if that's what we're going for. So there's different things we could do in terms of blending. We could also change parameters for how far ahead we were predicting, how obstacle avoidance is handled, the weights. If we're doing blended steering behaviors, what are the actual weights that we're using? Maybe priorities if we're using some kind of arbitration scheme. But we also have control over the performance envelope of the agent, especially if we are directly implementing the agents. So in that case, we can set unique maximum velocity or angular velocities. Same with acceleration, we can set. Or if we're using like a fancy animation system with root motion, of course, the animations that we use, that will create unique movement for the character. So even though a lot of the underlying algorithms are the same, maybe across many different agents, we still have a lot of freedom. There's a lot of flexibility in how we mix and match through blending, and how we define the performance envelope of the agents to get unique sorts of behaviors, and therefore this allows us to apply these techniques to lots of different types of games. A little bit more about selecting steering behaviors is that it's also important to realize how you can apply steering behaviors leveraging the rules of the game. So, for instance, let's say we have a game where the human player is the prey and they're trying to get to the bag of gold. And then we have an agent, the predator, that guards the gold. So in this case, the steering behavior would be maybe we try to determine a midpoint between the prey and the gold. And so that is a very simple exercise. We know how to define relative position vectors, and we could just find a point halfway along the relative position between the prey and the gold. And then we could have the agent always trying to move to that midpoint so that basically the predator would be guarding the gold, making it more difficult for the player to achieve that goal. Something else I wanted to mention about steering behaviors is that a lot of the techniques of steering behaviors were originally designed and developed by Craig Reynolds, and he wrote some different papers. One I've got a link to here for a web version from Game Developer Conference in 1999 that you can check out. There's also a website that has a lot of details about his work, and he implemented a lot of his work in a software package written in C called OpenSteer. And OpenSteer has been around for a long time as a very popular project to port to different languages. So if you're not interested in the C code, you can find it ported to Java, C#. I think there's even some of the code has been ported to Unity somewhere I've seen before. I think it's in JavaScript, all sorts of different implementations of the OpenSteer project. And there's demonstrations of all of the steering behaviors that we've talked about pretty much that you might find interesting. So I'm going to demonstrate this code real quick. Let me set this up, switch out from PowerPoint over to OpenSteer. So this is just a compiled version of the OpenSteer project. It is written in OpenGL using Glut, which is a little simple wrapper so that you can run windowed OpenGL. So the graphics are very primitive, but it does a good job of demonstrating. Now, one thing interesting about these examples is that there is no physics engine. There's collisions are not enforced. Everything that you see is just based on the AI behaviors. This first example that I'm showing, this is capture the flag. The little bluish purplish triangle there that's staying centered in the screen, that is the flag seeker. And then there are the guards, which are those kind of pinkish triangles. So they're chasing the flag seeker. And if they tag, then they win, and the trial is over and it restarts. So the flag is in that white circle. And it looks like we may have lucked out and entered an orbit. So the flag seeker is seeking the goal while being chased by the guards. There's no collision detection enforced with the guards, and there's no separation force either. So actually all the guards are currently superimposed on one another. But we've talked about the orbit problem before. there is no code in this example for capture the flag to deal with the orbit problem. I think there is a slight processing around. It's kind of hard to see, but yeah, because of the fact that the flag seeker wasn't able to take a direct line on the flag, and that was because it was evading at that point, the guards. That when it did finally re-enter the flag seeking exclusively, it was within the turn radius. So this just demonstrates how easy this problem is. I think I can reset with, let's see if R is the right key. No, maybe I don't have focus here. Yes, R is correct. So restart our session here. All right, so the hollow circles, those are obstacles. And if the flag seeker gets too close to an obstacle, it will steer around. Same for the guards. They will also attempt to avoid. Now, they're not always successful. If you watch long enough, eventually either the flag seeker or the guards will cross into the obstacles. So here's a case where the flag was successfully grabbed. Now, the strategies that the flag seeker uses are selected by a state machine. So there is arbitration in the form of a simple state machine. And you can see the states written in text over the agent. So you see like seek and evade. That was a blended steering behavior at that point. And then there's a state for seek goal. And in terms of deciding how long to seek, the green outline shows a corridor. We'll see if that green corridor pops up again here in a second. But the green corridor is checked to see if there's any guards within it. And if the guards show up within there, it will switch to seek and evade, or perhaps exclusively evade. So I think we're in an orbit again. But yeah, it's pretty interesting. Of course, you can check out all the code to this example, and there's a few other examples as well. Let me switch here. So if you hit Tab, you can go to the next example, and this one is a group behavior. Pedestrians, like NPCs walking on sidewalks, perhaps. And so the red lines are the paths to follow. They're trying to avoid running into each other. And there is also obstacle avoidance. And you can see all sorts of different visualizations that reflect the different strategies and calculations that are taking place. And so these are similar to like the cone strategy we saw before. So checking the angle, I think that is one of the approaches that are used. And then I think there's a different approach used for the obstacle avoidance. That occasionally there are the obstacles, the fixed position obstacles. But this is interesting to see. And of course, this is all running very efficiently with a large number of pedestrians. In the top left, if you can read the text in the video, there's some options there with you hit function keys to change the crowd size, for instance. Let's see if I can increase real quick, just see what happens here. I'll hold down. So this was written many years ago, so it should be able to handle quite a number of pedestrians. So I went from 100 to almost 400 here. So it's quite a mess. Still running pretty efficiently. And also there is a setting for using a bin lattice. And so that is a space partitioning scheme. And all of these agents they belong to different bins in this bin lattice, and they're transitioning from one bin to the next. And then when they're checking for neighbors to avoid, it's looking in that neighborhood. So you might recall from previous lecture videos, you look at all the adjacent cells if you're using the bin lattice strategy. So yeah, this is now quite the mess, but it's still working. As you look at the video, look for agents to completely run over one another, which is happening quite a bit here now. And that is because, again, physics is not being enforced. All of the avoidance that's occurring is just based on the AI strategies alone. But of course, that can fail. It's not, the steering behaviors don't have guaranteed outcomes. I'm going to skip to the next one. This is an example of boids. So the boids are like a school of fish or a flock of birds. They like their friends, and they identify friends by someone going in the same direction as them and the same speed. And if they find a friend, they will be attracted, but if they get too close, they'll separate. And if you let this example run long enough, they will they'll all group up together as they move around. So I just increased a bunch more boids, and you can see it's still running efficiently. This is also using a bin lattice, and in this case, I believe it's now a 3D bin lattice instead of 2D, because the boids are moving around in 3D, like swimming through water or flying around. But we'll talk more about boids when we get to group behavior as a topic for lecture. And let's see, I will hit tab again. And some of these are really more demonstrating smoothly animating the animation parameters, or the position according to velocity and acceleration. Now this example is a strange one. There is a seeker that wants to eat all the other agents, and then those agents themselves want to be eaten. So it's just demonstrating the prediction capability that you can use with steering behaviors. But it's really strange in terms of a scenario that you might ever want in a game. I don't think it's really realistic for a video game, other than just demonstrating some of the algorithms. This next one is just showing the smooth animation of turning. Another one with turning. Again, just showing how smoothly the update of the steering behaviors is over frame to frame. And this one's interesting. It's like a slow turning tank, and it's using a more advanced form of collision detection or for obstacle avoidance than what we've discussed so far. Instead of casting a ray, this agent casts arcs based on the current turn rate. So that is more accurate. That more accurately represents the current path of the agent or the tank in this case. And those act like whiskers. So they're tested for intersections with obstacles, and then the agent can decide based on the distance to impact whether it needs to slow down in order to make a tighter turning radius or to speed up. And it's not perfect. You'll often see this vehicle will crash. Maybe it'll crash right here, I think. Oh, just barely. Surprised it survived that one. But yeah, this is, I think, a pretty neat example. I like how it uses the curved rays rather than linear. And this works well when you have such a slow turning rate and therefore a very large turning radius. It's more important to be very precise about future predicted collisions. I'm going to skip to the next one. So this is the last example. This is a way to test out robot soccer. So you've probably heard of the competition where the robots play a soccer game. I think it's like usually once a year. Well, this was like a starter for early versions of the robot soccer competition. And this example is really pretty primitive, but you could use it as a starting point for prototyping in software. And so you'll see that these agents, they have like little simple state machines. If the ball is close, which is the green triangle, the agents will go try to just bump into it with little thought of where it's going to go. But if the ball gets too far away, they go back to their home positions. So they'll often score goals on their own team rather than the opponent. But yeah, so this OpenSteer software package is really interesting to check out. It's helpful for understanding steering behavior implementation, and you can often, like I said before, you can often find it implemented in your favorite engine, and maybe even for your game engine if you're using a game engine. So let me go back to the slides. Last slide here, just to summarize steering behaviors. Steering behaviors is a simple but powerful technique for implementing real-time agent movement. It's especially good for handling local movement. It is, however, susceptible to getting stuck. Your agent using steering behaviors is susceptible to getting stuck in equilibrium or not performing behavior with a desired outcome based on especially constrained environments that we saw examples of before. And more advanced agents that rely on steering behaviors will also need support of a higher level planning system. So really, you can only get so far with steering behaviors. You often will need to couple your steering behaviors with something else, like a finite state machine, perhaps. And so that is the direction we'll be going. So we'll need that sort of reactive decision making coupled with the steering behaviors, and then probably also leveraging the path planning strategies that we've already looked at.